Hello University of Melbourne students. Welcome to the first video in a series which explores the different engineering degrees on offer by the University of Melbourne. This video explores the mechatronic engineering discipline and what you get to look forward to if you plan to study it at Uni Melb. But first, what are mechatronics engineers? Mechatronic engineers are multidisciplinary engineers. We work with mechanical systems, electrical systems, fluid-based systems, and of course software, which can tie everything together. With the world becoming increasingly digitized, there is more and more space for mechatronics engineers. Mechatronics engineers are often found working in the fields of robotics, automation, sensors, and systems integration, to name a few. You always hear about different fields of engineering, but never what an engineer actually does day to day. What does an actual mechatronics project look like? In the subject Autonomous Systems Clinic, engineering master's students work to build an autonomous warehouse robot. The high-level goal is to collect different kinds of objects from dispensers and deliver them to various receptacles. Now, that doesn't sound so difficult, but how does the robot know where it is? What happens if it gets bumped off course? What if there are areas of the warehouse it's not allowed to drive? Each of these problems is a rabbit hole of challenges that engineers need to solve in order to have the robot not just work in a single warehouse, but many different warehouses. The main goal that we need to think about is how do we get the robot to move from one point in the warehouse to another point in the warehouse while avoiding obstacles, and this can be broken into three smaller challenges. Challenge number one is to plan the robot's trajectory. How can we create a path which the robot will travel along to achieve its goal? Challenge number two is robot localization, which means knowing where the robot is in real time. And challenge number three is to develop a control system for the robot, so that given a path, it can follow it accurately. Let's have a look at this first challenge, trajectory generation. The way we create a trajectory or path around the warehouse for our robot is by first converting the physical layout of the warehouse into a graph of waypoints, which represents the allowable space the robot can move in. Then we implemented graph traversal algorithms to find the shortest path between any two of these points. These algorithms are taught in the second year subject, Algorithms and Data Structures. So now we know the path the robot should be taking. But how do we know where the robot exactly is? This brings us to our next challenge, which is calculating the robot's current position based on the movement of its wheels. To measure the movement of each wheel, two encoders are used to send signals to the main computer. A simple example of how the computer processes these inputs is if the right wheel is moving forward and the left wheel is moving backwards, you know the robot is just turning on the spot. To model this differential drive robot to find the mathematical equations that govern it, concepts were built upon from the master's level subjects Control Systems and the undergraduate subject Systems Modeling and Analysis. So now we know the path the robot should take and exactly where it is. But what signals should we send to the wheels so that it follows this path correctly? What happens if the robot veers slightly off course? How do we make sure that it actually sticks to this planned path? First, we can calculate various types of errors based on where the robot is and where it should be. And then we can turn these errors into electrical commands that are sent to the motor via closed-loop control architectures, which we'll learn about in the master's subjects Control Systems and Advanced Control Systems. To help us solve all these challenges mentioned so far, we've utilized two main software tools. We first used MATLAB to model our physical system and to simulate our proposed algorithms to make sure that they performed as expected. And then to implement our algorithms on the physical systems, we used something called ROS, the Robot Operating System. ROS allows complicated robotic systems to be broken down into smaller programs called nodes, making it much easier to work on. Unfortunately, the system that we've just discussed isn't perfect. Do you remember those localization techniques I discussed before? Well, it turns out they're only good for short distances. When the robot's tires have been mismeasured or the wheels slip, our estimate for where the robot is will be inaccurate, and that inaccuracy will grow over time. To fix this problem, we'll take advantage of computer vision by installing a camera onto our robot. Computer vision is a form of artificial intelligence, in which a robot is trained to interpret and understand the visual world. It's a big challenge to distinguish between day-to-day objects, but we can make use of physical markers called Aruco markers, which look very similar to QR codes. If we know the physical position of all these different markers in the warehouse, we can figure out where the robot is if the camera can see these markers. Computer vision has come a long way in the past decade, and there now exists pre-built libraries for both calibration and integration of computer vision systems. OpenCV is one such example of this, and it's currently the most used computer vision library, and it's compatible with ROS because it uses the Python programming language. The subject, Sensor Systems, in the Mechatronics Master's degree, touches on the theory behind computer vision and some of its applications. Our final challenge for this project is to design the payload system. How do we load, carry, and unload different sized objects? So we applied our mechanical engineering skills that we developed during mechanical systems design, a subject in the undergraduate degree, to design a payload system. First, we came up with several different design concepts and went through some iterations to arrive at our final design. When the design was ready for fabrication, we generated a sheet metal drawing and went through the extensive workshop training that allows us to use tools such as grinders, laser cutters, 3D printers, and sheet metal cutters, and much more. Our storage mechanism is made of one piece of sheet metal, which involved cutting and sanding the sheet metal into shape using sheet metal grinders and benders. Then we used circular saws and hand drills to fabricate the mounting mechanism for the storage box so that it could be properly mounted to the robot. You're now seeing a video of the final prototype in action, and while it has some bugs in its behaviour, it can perform the tasks set out for it. We hope this has been a good showcase of the skills that you will learn during your degree at the University of Melbourne, and why they might be useful in real-life applications. Thank you for watching.